Okay, so now we will draw the velocity triangle for this. So how would be the velocity triangle now? So we will draw the vane here, the blades. As I told you, it is double ellipsoidal in shape. Okay, and the water jet is entering from this point, at this point. Okay, now the velocity, as I told you, the velocity with which it is entering is, it is hitting the blade is v1. Okay, and suppose the velocity of this blade is u. Okay, so this will be, okay, and the relative velocity will be vr1. Getting this? Velocity with which the jet is hitting the plate at center is v1. Okay, and the horizontal component of this v1, as I told you in the previous unit we have discussed, the horizontal component of this v1 is nothing but vw1, velocity of whirl. Okay, I think you have remembered this. Getting this? And the velocity of this blade is u. Okay, and therefore the relative velocity at inlet is vr1. Okay, now similarly the relative velocity at outlet is, suppose, vr2. This is relative velocity at outlet. Okay, now let's suppose alpha 2 is greater than 90 degree. Okay, and this alpha 2 actually depends on the runner speed. If the runner speed is slow, okay, for a slow runner alpha 2 is less than 90 degree. For medium runner alpha 2 is equal to 90 degree, and for fast runner, that means if runner is moving very fast, this alpha 2 will be greater than 90 degree. Okay, now what if alpha 2 is greater than 90 degree? Okay, so if the alpha 2 is greater than 90 degree, I will get vr2 in this v2 in this direction. So this will be v2. Okay, this angle is alpha 2, this angle is nothing but alpha 2. Getting this? Okay, now the horizontal component of this v2, as I told you, is nothing but vw2. Horizontal component of this v2 is vw2. Okay, and this total, it means between this vr2 and u2 and v2, we will get u2 or u. Okay, u is same at both points because the distance between these 2 points are very less. It is negligible distance. And as we know, v is equal to omega into r, the radius is almost similar, so we assume here the velocity u of the runner is same at both the points. Okay, so this is how the velocity triangle will be. Okay, and this angle will be beta 2, this angle is nothing but beta 2. Getting this or not? Okay, now we so this angle beta 2, blade angle at outlet, okay, and if we extend this up to this point, this angle is nothing but theta, which is equal to 180 minus beta 2, and this theta is nothing but jet deflection angle. Okay, the angle beta 2 is blade outlet angle of the blade, and this angle theta is nothing but jet deflection angle, which is equal to 180 minus beta 2, and this theta is generally equal to 165 degree. Now why this is 165 degree, almost equal to 165 degree, we will discuss. Okay, so this angle theta is almost equal to 165 degrees. Okay, now if we want to determine the force by this jet on the blade, so that force, as I told you, is m into vw1 minus vw2. This will be force. Okay, now what would be power developed, or you can write it as m can be written as rho into q vw1 minus vw2. Okay, this is force. Now what will be power? So power developed is nothing but f into u. Okay, so the power developed f into velocity, okay, whatever velocity it is moving, so this power developed p will be equal to f, which is rho q vw1 minus vw2 into u. Getting this now? Okay, this will be power developed. Now if I want to determine the work done, what will be work done? okay, or you can write it as this power developed or work done per second is equal to rho A V1 into VW1 minus VW2 into U. Getting this? This is the power developed by this blade. Now what will be the efficiency of the blade? Very important thing. So what will be the efficiency of the blade efficiency? Okay, now what is blade efficiency? This is nothing but work done by at wheel divided by kinetic energy of jet. Okay, now why this is the blade efficiency? Blade efficiency is nothing but output of the blade divided by input of the blade. The output we are getting is nothing but the runner power. This is nothing but the runner power. This is the output of the blade, and input, this blade is getting input in the form of kinetic energy of the jet. Okay, so the blade efficiency will be equal to work done at wheel divided by the kinetic energy of the jet. Getting this? Or further this can be written as rho A V1 into VW1 minus VW2 into U divided by kinetic energy of jet, which is nothing but half mv square, and m can be written as rho A V1 into V1 square. Getting this? Okay, so further this rho A V1 and rho A V1 get cancelled out, and we will get what? This will be 2U VW1 minus VW2 divided by V1 square. Okay, this is the case when we are considering this alpha 2 as greater than 90 degree. Okay, if alpha 2 is less than 90 degree, the velocity triangle would be like this. The inlet velocity triangle would be same. Okay, now how would be the outlet velocity triangle? I will draw it here only. If alpha 2 is less than 90 degree, then the outlet velocity triangle would be like this. This is VR2, this will be V2, this is nothing but VF2, and this is nothing but alpha 2. That means alpha 2 is less than 90 degree. Getting this or not? Okay, and this the component of this V2 in horizontal direction is nothing but VW2. So this will be VW2. Okay, and the distance between this VR2 and V2 is nothing but U. So this is nothing but U. Okay, so this would be the velocity triangle if alpha 2 is less than 90 degree. Getting this or not? Okay, now very important thing, if alpha 2 is less than 90 degree, then as I told you we have already discussed, then it would have been plus VW2. Okay, if alpha 2 less than 90 degree, then efficiency will be equal to 2U VW1 plus VW2 divided by V1 square. This would have been difference. Okay, or you can write it as efficiency of blade is equal to 2U VW1 plus minus of VW2 divided by V1 square, depending upon the value of alpha. Okay, so initially we are considering this only. Okay, that means the alpha 2 we are considering as greater than 90 degree, and we will analyze with this result. Efficiency is equal to 2U VW1 minus VW2 divided by V1 square. Okay, now further this can be written as what? Now this VW1 is equal to V1. Okay, just write it. I am writing it here. VW1 is equal to V1. Now what is VW2? What is VW2 here? So VW2 can be written as U minus VR2 cos of beta 2. Okay, VR2 cos of beta 2, that means this distance U minus VR2 cos beta 2 is nothing but VW2. Okay, so from here this VW2 will be equal to U minus VR2 cos of beta 2. Getting this? Okay, now as I told you that this VR2 by VR1 is equal to K, where K is less than 1. Okay, or you can say VR2 is equal to K into VR1. So just put the value. So this VW2 will be equal to U minus K VR1 into cos of beta 2. Getting this or not? Okay, now further this VR1 can be written as, what is this VR1 here? This VR1 is equal to VW1 minus U. Okay, you can write this VR1 as VW1 minus U or V1 minus U. Getting this? Okay, so just put the value. So this will be equal to U minus K into V1 minus U into cos of beta 2. Okay, this, as I told you, we are considering this case. That means alpha 2 is greater than 90 degree. This case we are considering. Okay, so what will be the efficiency? So now this efficiency will be equal to efficiency is equal to 2u Vw1 minus Vw2 by V1 square. Okay, so just put the value, we will get what? 2u Vw1 is nothing but equal to V1 minus Vw2, which is u minus minus plus into k cos of beta 2 into V1 minus u. Getting this? Divided by V1 square. This is nothing but efficiency. Okay, now further this can be written as what? So from here we can write it as 2u, take V1 minus u as common, so this will be V1 minus u, and inside we will get what? 1 plus k cos of beta 2 divided by V1 square. Okay, this is the value of blade efficiency. Okay, now further this can be written as, so this blade efficiency will be equal to 2 into 1 plus k cos beta 2, okay, into, now this can be written as u into V1 by V1 square, u V1 by V1 square minus u square by V1 square. Okay, now considering one term here, so we will consider, take u by V1 is equal to rho, and this rho is nothing but blade speed ratio or ratio of bucket to jet speed. Getting this? U by V1 is taken as rho here. Okay, 1 V1 will be cancelled out here. We will be left with u by V1 minus u by V1 whole square. Okay, so this term, this efficiency term eta b will be equal to 2 into 1 plus k cos beta 2 into rho minus rho square. Okay, so this is the value of efficiency in terms of rho. Now why we are finding this efficiency in terms of rho? Because here k is a constant, beta 2 is also a constant, that means the only variable on which this efficiency is depending is nothing but rho. Okay, now if we want to determine the maximum efficiency, what we will have to do is we will just differentiate this efficiency with respect to rho and equate it to 0, and finally we will get the value of rho for which we will get the maximum efficiency. Getting this or not? Okay, so for maximum efficiency, d eta b by d rho, this should be equal to 0. Okay, or you can say this will be 2 into 1 plus k cos beta 2. Okay, now differentiate this with respect to rho, this will be 1 minus 2 rho is equal to 0. Okay, or you can say rho is equal to 1 by 2 from here, rho is equal to 1 by 2, or you can say u by V1 is equal to 1 by 2. Okay, or you can say u is equal to V1 by 2. Okay, so this is the condition for maximum blade efficiency. So for maximum blade efficiency, this u should be equal to V1 by 2, very very important thing, or rho should be equal to 1 by 2. Okay, so this is the value of rho for maximum efficiency. So in order to get the maximum efficiency, just put the value of rho here, we will get maximum blade efficiency. Okay, so maximum blade efficiency will be equal to what? Maximum blade efficiency, this will be equal to 2 into k cos beta 2, sorry, 2 into 1 plus k cos beta 2. Okay, just put the value of rho 1 by 2, so this will be 1 by 2 minus 1 by 4. Okay, so this will be equal to, this 1 by 2 minus 1 by 4 is 1 by 4, it will 1 2 will get cancelled out, and we will get what? 1 plus k cos beta 2 divided by 2. This is the maximum blade efficiency, expression for maximum blade efficiency. Getting this now? Okay, now how would be the variation of this efficiency? This efficiency is varying with respect to rho as eta b is equal to 1 plus k cos beta 2 into rho minus rho square. That means at a point, if I draw the graph, between blade efficiency and the value of rho, which is u by V1. Okay, I will get a parabola with maximum efficiency as 1 plus k cos beta 2 divided by 2. Okay, so I will get one parabola here like this. This is the variation of efficiency with respect to rho. Getting this? Okay, so this is okay. So this is the graph, and the value of rho at maximum efficiency, as I told you, is 0.5. Okay, and for this efficiency to be maximum, now further, if this for this efficiency to be maximum, the first thing should be that K should be equal to 1. Okay, K is the friction factor. This friction factor should be equal to 1. First thing. Second thing, this beta 2 should be equal to 0. Okay, because when this beta 2 is equal to 0, this cos of beta 2 will be equal to 1, and we will get the maximum efficiency 1 plus 1 by 2, 2 by 2, which is equal to 1. That means 100% efficiency. Okay, so if K is equal to 1 and beta 2 is equal to 0, the efficiency, blade efficiency, will be equal to 100%. Getting this? That means if I draw this graph for K is equal to 1 and beta 2 is equal to 0, I will get what? 100% efficiency. 1. Getting this? Okay, but is it possible practically to have the value of beta 2 as 0? Let us see. Okay, so as I told you, the value of beta 2 is equal to 0. What does this mean? Beta 2 is equal to 0. That means this outlet jet will be in this direction, in horizontal direction. So this is the condition when we will be getting 100% efficiency, if K is equal to 1 and beta 2 is equal to 0. But is this possible practically? Obviously not. Why? Because if this value of this beta 2 is equal to 0, this blade will hit the jet in the corresponding blade. Suppose this is our blade. If this is moving at 0 degree, if the jet is moving, outlet jet is moving with 0 degree, it will hit the कमिंग ब्लेड, एंड जो दूसरी ब्लेड है उसमें हिट करेगा वो, और उससे क्या होगा? इट विल रिटार्ड द मोशन ऑफ दैट ब्लेड. Getting this or not? Okay, so this actually is not possible. Having beta 2 is equal to 0 is not viable, not possible. Why? क्योंकि अगर beta 2 equal to 0 हो गया तो वो further फिर coming blade में hit करेगा, वो jet coming blade में hit करेगा, and finally it will retard that motion. Okay, so value of beta 2 should not be equal to 0. So at least उसकी कुछ value रहनी चाहिए. Obviously जितनी कम हो उतना ज़्यादा अच्छा है, but उसकी कुछ value रहनी चाहिए, and that value, that optimum value of that beta 2 should be equal to 10 degree to 15 degree. And according to this 15 degree, if this beta 2 is 15 degree, then this theta should be equal to 165 degree, as I told you in this figure. Okay, if this beta 2 is 15 degree, then this theta should be equal to 165 degree. Okay, so this is the reason why this theta should be equal to, is approximately equal to 165 degree. Getting this or not? Okay, and when this theta or beta 2 is equal to 15 degree, obviously this rho will not be equal to 0.5, and this efficiency will not be equal to 100%. Efficiency will be little less. Okay, so the optimum value of efficiency which is obtained is 0.93, and which is at rho is equal to 0.46. So when this theta is equal to 165 degree or beta 2 is equal to 15 degree, this rho is equal to 0.46, and the efficiency, the maximum value, or you should say optimum value of this efficiency, is 93%. Getting this or not? Okay, now few more things to understand in this Pelton wheel turbine. Now if the diameter, if mean diameter is D, if mean diameter of the runner is D, mean diameter, what is the meaning of this mean diameter? You can see here the pitch circle, you can see. Okay, so this is our pitch circle. So what will be the mean diameter here? So if the diameter of this pitch circle is nothing but mean diameter. Okay, not the inner diameter. Diameter of this pitch circle is nothing but mean diameter. Okay, so if mean diameter is D, then obviously this U will be equal to pi d n by 60, where n is in RPM. First thing. Okay, one more thing while considering the designing, that is Tegan's formula. Tegan's give formula for number of blades, number of buckets, how much buckets should be kept in this Pelton wheel turbine, so that number of buckets Z should be equal to capital D by 2D plus 15. Okay, where capital D by small d is equal to m, which is nothing but jet ratio. Okay, what is capital D? Capital D, as I told you, is pitch circle diameter here, and what is small d? Small d is nothing but the diameter of this jet. The diameter of jet is small d. So the ratio of this capital D by small d is jet ratio, and Z is equal to d by 2d plus 15, or you can say this Z is equal to 0.5 m plus 15. Okay, so this is important consideration while designing this Pelton wheel turbine. Getting this now? Okay, now one more thing, total discharge. Total discharge Q, what should be total discharge? Q, this should be equal to, what will be total discharge here? So this total discharge Q is equal to pi by 4 into d square A into V, and velocity here with which this jet is striking is V1. Okay, so this total discharge will be equal to pi by 4 d square into V1. Okay, now if suppose we are having n number of jets here, so for n number of jets, this Q will be equal to pi by 4 into d square V1 into n. So for n number of jets, total Q is equal to pi by 4 d square V1 into n. Okay, now coming to the efficiencies of turbine, very important thing. Okay, the very first efficiency is the nozzle efficiency. Okay, so one thing I told you students, the total power available here, I will tell you with the help of this diagram. Just understand this thing very carefully, and once you understand this, you will be able to find each and every type of efficiency very easily. Okay, so as I told you, the total power available at this point is nothing but water power, and what we gave the name as this is water power, and which is equal to rho GQ into Hg, which is gross head. Okay, now there are certain losses, and after those losses, the power, the water power which is available at entry of nozzle, the water power which is available at entry of nozzle is nothing but rho GQ into H, where this H is nothing but the net head, as I told you yesterday. Okay, so the total power which is available at the entry of nozzle is rho GQH. Now there are certain losses in nozzle, and after that this nozzle is leaving the water, the energy we are getting outside the nozzle in the form of kinetic energy only. So inside nozzle we are having this energy rho GQH, and outside nozzle we are having the energy as complete energy as kinetic energy, which is half mvv square. Getting this? So this water power, this power is converted to kinetic energy through nozzle. So if I want to determine the efficiency of nozzle, so what will be the nozzle efficiency here? So nozzle efficiency is output of nozzle divided by input of nozzle, output by input. Okay, what is output energy here? Output energy is nothing but kinetic energy, which is half m v1 square divided by input is rho GQ into H. Okay, now further this m can be written as rho into q. This is half rho q v1 square divided by rho GQ into H. This rho q get cancelled out, and we will get nozzle efficiency as v1 square by 2 into H. v1 square by 2gh. Getting this or not? Okay, now one more thing I told you, what is v1? v1 is equal to cv root 2gh. Okay, or you can say v1 square is equal to cv square into 2gh, or cv square is equal to v1 square by 2gh. Okay, so this nozzle efficiency eta n can also be written as cv square. So this nozzle efficiency is equal to v1 square by 2gh, or is also equal to cv square. So first is the nozzle efficiency. Now after nozzle, this is getting into runner. Once it crossed the nozzle, then this jet of water having kinetic energy half mv square, this is entering into runner, and from this runner we are getting some power. From these blades we are getting some power. So input to the runner is nothing but the kinetic energy, and output of this runner is nothing but the runner power. So if I want to determine this blade efficiency, the blade efficiency, so what will be blade efficiency now? So second type of efficiency is nothing but blade efficiency. Okay, wherever there are losses we can determine the efficiency. So what will be the blade efficiency here? Again, output of blade divided by input of blade. Now what is the output of blade here? So the output of blade, as I told you, is nothing but runner power, okay, divided by input of blade is nothing but kinetic energy, which is half mv square. Okay, now what is the runner power? So runner power, again we have determined. Okay, so this was our runner power. So this will be equal to rho a v1 vw1 plus minus of vw2 into u divided by half m can be written as rho a v1 into v1 square. Okay, so this rho a v1 will get cancelled out and we'll get blade efficiency is 2u vw1 plus minus of vw2 divided by v square. Okay, so this is the blade efficiency, second type of efficiency.